everybody to today's Flow Talk. As you'll know, Flow stands for Federated Learning One World Seminar. It's roughly running once a week with some exceptions during conferences, important deadlines, and so on and so forth. And we try to cover and will try to cover all aspects of federated learning, whether this is related to systems, algorithms, privacy, or any other considerations. Today is a great pleasure for me to introduce Grigory Malinovsky, who's a PhD student in my team at KAUST. And he will talk about server-side step sizes and random reshuffling or sampling without replacement, and the role of these tricks in federated optimization. Grisha, you can tell us whether you would welcome questions throughout or at the end, how you want this to be run. What is your preference?
Okay, I will tell this preferences. Okay. So if you have any questions, please ask it like immediately. It would be easier for me to answer like soon as slide appears. It's not convenient for me to read the chat, so do not hesitate.
Me and Samuel will be observing the chat, so if something happens, we'll just alert you to this and we'll unmute the person as we typically do. Okay, so take it away.
Okay, thank you, Peter, for your nice introduction. Okay, hello everyone. It's a really great pleasure for me to give a talk on this seminar. Okay, today I'm going to discuss how server-side step size and sampling without replacement, also known as random reshuffling, can help in federated learning. Okay, this is okay. Okay. This is joint work with Konstantin Mishenko, who got PhD at KAUST. Now he is in France, and Professor Peter Starik. So this is the tentative plan of my talk. Firstly, I'm going to remind what federated learning is in general. Then I will compare and discuss the most popular method for federated learning, which is local SGD, and it's also known as federated averaging, and its alternative, which is federated random reshuffling. After that, I will introduce our new method, and I will consider two types of analysis for large and for small server-side step sizes. And lastly, I'm going to show some experimental results. Okay. Okay, let me remind what is federated learning in general. Federated learning is a general framework for distributed learning that allows us to avoid sharing client data. Federated learning is a relatively new topic, but it has many applications such as medicine, Internet of Things, natural language processing, and many more. Federated learning, as Peter mentioned, can be studied from different perspectives. It includes many aspects such as privacy, security, systems, and so on. In this talk, I'm going to discuss optimization aspects of federated learning. Okay, let me explain the setting what we are dealing with. We consider the centralized regime of distributed learning, which is, I believe, the most popular approach in federated learning. In this setting, the data are distributed across many clients, for example, phones, or I don't know, refrigerators. And each client has its own local model and can update its local model using local data. Transmitting data is not allowed because of security and privacy. And client can send their model updates to central server, and communication between clients is not allowed. we have communication only between server and client. Okay, server aggregates local updates received from clients and update the global model. And after that, server sends this global model back and this process repeats. Okay, let us consider mathematical formulation. Our goal is to solve a finite sum minimization problem, which is a basic problem for solving empirical risk minimization. Here we have M, which is number of machines or clients. D is the dimension of our problem, and FM is a local loss function. Each client has own data set, so local loss can be represented as another finite sum of individual loss functions, and N here is a number of local data points. For simplicity, we assume that each client has the same number of data points, but these results can be generalized to different number of local data points easily. Okay. Now I want to highlight some key characteristics of federated learning. The first aspect is that local methods are extremely successful in federated learning tasks, and recent papers show that some additional step after aggregation can be also beneficial. The second aspect is that usually we have high level of heterogeneity since each client has its own data set, and we do not desire to have some similarity assumptions, and this heterogeneity leads to some algorithmic problems. Another problem is that in practice, only few clients can participate at each round. Because, for example, if we have million of phones, it's impossible to force them to communicate together at certain time point. So this means that algorithm should use some client sampling technique, which cause additional variance. Okay. Also, communication
I
compression.
can see a question
Okay.
here by KMD. So let's. Okay. I believe you can unmute yourself now. Kirandi.
Okay. So as far as I know, generally at server we just aggregate whatever is updated, whatever updates are sent from the local clients. So when it is written here global steps, what does that exactly means?
Okay, I will explain it later because
Okay, sure.
I have like several slides explaining this question. Sorry for this. Yeah. Okay, can I continue?
Yeah, go ahead.
Okay. So in federated learning, the communication compression is very important ingredient because federated learning is known for communication bottleneck, and additionally to data heterogeneity, we have client heterogeneity, which means clients have different characteristics such as computational capacity. We also should care about privacy and security in federated learning, but in this work, I'm going to focus on first three aspects. Okay, let's move on. And now I'm going to describe the main idea of local methods. At the beginning of local computations, server sends the global model XT to each client, all copies of this model. Each client perform local computations, and after some steps, server aggregates the local models, and the simplest way to do is to just average the models. So for simplicity, we assume that number of local steps is equal to number of data points. In other words, each client does a local epoch before aggregation, or the full pass through the dataset. Of course, we can do early stopping, or we can do several epochs, and we can generalize our analysis to this setting. But for simplicity, let us assume that number of local steps is equal to number of local data points. Okay, so local SGD uses stochastic gradient step, usually with uniform sampling of data points. Of course, we can use some mini batching or other techniques such as importance sampling. But the main thing that this stochastic gradient is unbiased. But alternatively, we can use random reshuffling. The main difference is that at the beginning of each epoch, each client samples independently a permutation and performs updates according to this permutation, and each function is used just once per epoch, so we do not have any repetitions, which can be in SGD method. Okay, and the aggregation process is the same as for local SGD. We just average our models, and this process repeats. Okay, so local SGD and federated random reshuffling are deeply analyzed in the following papers, and the main message from analysis for strongly convex case is that local SGD has rate O1/MT, but federated random reshuffling has N/MT squared rate, which means that federated random reshuffling outperforms local SGD for large number of epochs, basically when T is bigger than N. Of course, we have some cases when local SGD is better than federated random reshuffling, but if we have sufficiently large number of epochs, federated random reshuffling is more preferable choice. Okay, do you have any questions so far? I think
there are no questions in the chat or raise hand, so you can.
Okay, so I will continue. Okay, so the question is, can we do something better than federated random reshuffling? And let us consider the new algorithm, which is called Nastya. So the setting is the same. Server sends the model at the beginning of each epoch, and we use the same technique. We use random reshuffling update rule, but the difference, but we have different aggregation step here. Using updated local model XNTM, we can scale difference between updated local model XNTM and XT by factor of gamma n, and we can this GTM can be seen as stochastic estimator of local gradient of some client, and I will explain why later. So using these local gradient estimators, we can get global gradient estimator GT just using aggregation, and after that we perform additional gradient type step with server-side step size eta here. So the idea is not new. In these papers, authors introduced different methods with server-side and client-side step sizes, and these methods were analyzed. But I'm going to show that conjunction with random reshuffling, I mean, the idea of two step sizes with random reshuffling leads to much better convergence guarantees. Any questions? And did I explain the question what appeared earlier?
So, Kirandi, this was, I guess, a question for you, whether this answered your question about the aggregation.
Yeah, it's quite clear now.
Okay,
so
great.
So, I'll ask, just, can you just shed a little bit more light why the aggregation rule now doesn't aggregate these XTINs, but these scalar differences? What is intuition, if you can say it in different words? What is the intuition behind this? Why should one do that?
Okay, it would be in next slides, but
okay, good. Then you can just do it on the next slide.
But I mean, I can explain in high level because usually the basic method for distributed optimization is not local SGD, but just distributed gradient descent. And this method is working this way. Instead of sending models, we send local gradients, and server aggregates these gradients, and after that do gradient type step. So here we want to combine two approaches. I mean, local steps and gradient descent method, let's say global gradient descent method. So, and we will see benefits from this conjunction. So, did I answer this question?
Well, I guess you'll have. I'll wait for the next slide.
Okay.
Okay. Thank you.
Okay. Okay. Let us consider a large server-side step size regime, and for illustration, let me consider a 2D example. So here we have illustration of one epoch. So after n steps of random reshuffling updates, the updated local model can be written like this. So we subtract the sum of gradients. So, and using this point, XNTM, we can form a local gradient approximation for each client. And it's just, and if we put like the definition of X and TM, we can see that our gradient approximation is just average of permuted gradients, but evaluated in different points. So if we can evaluate these gradients at the same point, we will have just full gradient because of some structure. But here we evaluate gradients in different points. So and we can illustrate. So we can illustrate this local gradient estimates by dot lines. So is it clear? Okay, and now server performs additional step using large step size. So we do this gradient type update, and if we replace GTM by its definition and rewrite the update rule, we can see that the server side step from XT is just equivalent to additional jump from average point, which is illustrated as solid purple line so the jump would be green line in the direction of difference of average point and XT. And it is easy to prove that, okay. It is easy to prove that the client step size goes to 0 when the gradient estimates goes to true local gradients. So the intuition is the following. Additional server-side step size allow us to jump from average point in the direction of difference of average point and XT. And as we can see, federated averaging would be just a special case of this method if eta is equal to so I mean if beta is equal to 0 and if beta is equal to 0, then eta should be gamma multiplied by n. So any questions?
So this seems to be a key slide. So maybe it's a good idea to just really pause for a minute or two and allow people to think a little bit and ask anything they might want to ask rather than soldiering on. So let's pause, and everybody, I would encourage you anything. So there's already a question by Nikita. You can unmute yourself.
Okay. Thank you, Peter. Hello, Grisha. Haven't seen you for ages. I have one question about intuition between below beta. For cases, for border cases where our gamma is relatively small while approaching 0, does it mean that in that case we have no progress in changing from X subscript T to X subscript T plus 1? Or we have a simple step, just like a mini batch step?
Yes, so like the second option is right, because eta and gamma are not correlated. So we can have really small gamma step size, which is like arbitrary small, And we can still have a large eta step size, which means because we have like additional parameter beta, so that's why we can play with these two step sizes as we want. So they are not firm in this sense. So, and if we consider extreme case when gamma is arbitrarily small, we will obtain just simple distributed gradient descent. Because let's look at GTM. If gamma goes to 0, GTM goes to nabla FM at xt. Yeah, and I think it would be beneficial if I apply this lemma. Okay, and if we use nabla FM of xt here, we will just get simple distributed gradient descent with, let's say, eta is proportional to 1 over L. So did I answer your question? So Nikita raised.
Yes, that's pretty answers my question. So thank you, Grisha.
Okay.
Let's move on.
Okay, let's wait for some more questions, maybe one or two, and then we'll keep going.
Okay, let me add some explanations. So in some sense, we have a general framework for 3 algorithms for simple distributed gradient descent, as I mentioned before, when gamma goes to 0. If beta is equal to 0, we have just federated random reshuffling. And here we have something in between. Okay, can I continue?
Okay, so maybe I just add insight before you go to the next slide, and then you just can go. So one way you can think of this, I'm speaking to the audience here, is that if the step sizes are small, then all of these local reshuffling steps, so these black steps going to this xt1n or xt2n in this case, they will be a very, very, very good approximation of gradient direction, but not of the gradient, but not of its length. So they will approximate the gradient direction, but the length will be completely off. So if you add these purple vectors, you get something very close to the gradient, but not the length. And that's the purpose of the jumping step size or this global server step size, to correct for the length. That's just another way of saying the same thing that Grigory said already in a different way. Okay, that's all I want to say.
Yeah, thank you, Peter. Yeah, and I want to add that yeah, we keep this direction, but since we scale our GTM by gamma n factor, we get really tiny thing if gamma goes to 0, because when xt minus x ntm also goes to 0, but in limit we get just gradient. Okay, let me continue. Okay, let me consider the bound for the strongly convex case, and it would be, I think, illustrative. So we have three terms here. First one is a linearly decreasing term. So it's proportional to distance between initial model and our solution. The second term is local variance of a method. So it's variance of random reshuffling, and it's proportional to double sum of squared norm of gradients at the optimum. So it's pretty standard thing in these algorithms. So there is no surprise. And the third one is client drift. And this client drift is the error accumulated by a local method because of data heterogeneity. So since the number of local steps is not equal to 1, and since each function has own minimizer, like local methods can diverge in some sense, and this error is proportional to the sum of squared norm of local gradients at the optimum. So it would be 0 if local data sets are identical. And here we have a really interesting thing. We can see that second and third term are proportional to the client size step size, while a linear term depends only on server side step size. So we get a nice decoupling here of step sizes, which allow us to use as small as possible client side step size, gamma here, and use a large 1/L server size step size. And in limit, we get like linear convergence rate, basically. So if gamma squared would be proportional to epsilon, for example. So this means that we can have, in some sense, a variance reduction technique here by decoupling of step sizes. But if we use partial participation or client sampling, we will have additional term which is proportional to global server-side step size. And if this, and you can see that if C is equal, C is cardinality of subset participating, and if C is equal to M, this term would be 0.
So we seem to have another question by Nikita. Apologies that
yes, it's again about this scheme where we have an update constructed of a difference between 2 points divided by gamma and n term. So as you mentioned, we can make it as small as possible, but in practice, we meet another bottleneck named as computation precision. So we, in practice, can't make gamma as small as we want. If we would like to measure some sort of gradient estimation accuracy, or I dare say for this case, it's more reasonable to measure the decrease on each step. We can maybe verify that, for example, if we start from gamma 0 for a not so small value, and to measure decrease from this step on our global target variable, or the target function, I mean, and will start monotonely decrease this value. So I dare say there could be maybe one or several points that can be considered as optimal for us. And if we pass this borderline, pass this threshold, I mean, say, the decrease of our loss function, for example, will become smaller. It means that our steps worsens in quality. So have you some justifications about which values of gamma are reasonable for this
Can you please
method?
repeat the last question? Nikita? Nikita, can you please repeat the last question?
Yes, the question is, do you have estimates on optimal values of gamma? For example, optimal lower value. Do you have some experimental verification? Do we have some threshold between which we only get worse updates?
Okay.
Lower convergence as a result.
Okay. Yeah. So if we speak about computational error, we do not need, I mean, exact zero for gamma. So let me derive a complexity here. So we can say, okay, let's forget about additional thing here. So we can say that let the first term be smaller than epsilon divided by 2, and second and third term together also less or equal epsilon divided by 2. And if here we can say that gamma should be proportional to square root of epsilon multiplied by our constants, and that's it. So if epsilon is not super small, we can set this option for gamma, and it would be okay for our purposes. And here we can set eta to be 1 over L, and like the total complexity would be just like complexity of gradient descent kappa multiplied by log 1 over epsilon. So, but okay, of course, in practice, sometimes setting gamma to be proportional to epsilon is not the best option, and I will explain later why.
I can add one maybe thing that is somehow related to what Nikita asked. So if you were running these SGD steps with replacement and not without replacement, which is what is being used here. So here it goes through random reshuffling of the data. Then this red step size here, dependence on the step size will not be gamma squared, but gamma. So that's very, very important. And that's the power of using this reshuffling rather than SGD locally. Because if there is just gamma, then obviously for small step sizes, this term, this neighborhood is going to be much larger than if you use gamma squared. So gamma is 1 over 100, let's say, then gamma squared is much more smaller. So that is the effect of this reshuffling, and this helps the step size to not be so small, and still it has effect on essentially making this neighborhood small. So that's in addition to what Grigory already said.
Oh, yes. Thank you, Peter. Thank you, Grigory. But another question arises that does it mean that our gamma value, optimal gamma values, are bounded from below? Have you witnessed such phenomena in experiments? I mean that for this inequality, we can say that our gamma, our appropriate gammas for our method depends on accuracy of the method or desired accuracy we want to achieve.
So I didn't consider any lower bounds for gamma. It should be larger than 0, but we didn't have any other considerations about lower bounds.
So yeah, it can be considered later.
Yeah.
So I would add to this as well. So this theorem holds without any lower bound of gamma, as Grigory said, which kind of means what you're trying to suggest is a bad thing. That is, even choosing very tiny step size, it's completely okay. The method will work. There's absolutely no issue with the method if the step size is really tiny, because then the eta step size, the global, the server step size corrects for it. Okay, so somehow there's no issue with gamma being really tiny. Now, if you ask whether maybe in practice it might make sense to sometimes to not have gamma, completely infinitesimal, well, that might be the case, but this theory doesn't capture this.
Oh, thank you. That's the point. So we should continue, I guess.
Okay, thank you for your questions. Okay, let me continue. And okay, if we consider partial participation, let's say with uniform client sampling, we will get additional error term, which is proportional to basically eta, and it's proportional to client drift notion. So, and in this case, using a large server step size might be hurtful for us. I mean, hurtful in terms of complexity. So, and this means that we need to consider our options, and I will go on to do it right now. Okay, we also have theoretical guarantees for not only for strongly convex case, but for convex and non-convex. And as you can see, we have almost the same behavior of our inequalities. We have this decoupling with gamma squared for random reshuffling variance theorem, and also we have partial participation variance theorem, which is proportional to eta. Of course, we have some differences in the first term because we use different assumptions on function, but overall, like the main message is the same for all settings. So I think it's more or less clear. And let us discuss small server-side step size regime. And we have similar but slightly different picture here. Okay, as we mentioned before, we can form local gradient approximations using differences between xt and xntm as previous. And we also consider server-side update here. And we can put like we can replace GTM, but its definition in the update rule. And if we rewrite this update rule in specific manner, in specific form, like here, we can we can observe that if eta divided by gamma n less or less than 1, basically, we have just a convex combination of 2 points. The first point is just xt, like the initial model for this epoch, and average point, the average point of updated local models, and so we have two regimes. The first regime when eta divided gamma n is larger than 1, and we have jumping in the direction of this difference. And if eta divided by gamma n is smaller than 1, we have, let's say, negative jumping, or we have convex combination of 2 points. And this convex combination can help us in certain situations. So do you have any questions regarding this slide? I think no. So everything is clear. So in some sense, we have negative server-side step here, or some relaxation. Okay, let's move on. Let me consider also strongly convex case. So for this regime, we have different type of analysis. Here we allow for gamma to be large, and I mean large means 1 over L, proportionally 1 over L. And here we have also 3 terms. First term is term of linear decreasing. So the second one is proportional to alpha gamma squared, and second term is caused by partial participation, because if C is equal to M, it would be 0. And the last one, which is orange, doesn't depend on alpha at all. As we had previously. Okay, and so we have alpha, which is eta divided by gamma n, and let us assume that we have ill condition problem, and we can have this red approximation. And we also choose alpha to be less than 1/2. Okay, we can forget about the third term in this bound because it doesn't depend on alpha. And let us derive the optimal alpha in this case. Okay, we can replace this factor here and simplify our bound. So, and we have this and we have these two terms, And again, we can use the same trick, say that the first one should be less or equal epsilon divided by 2, and the second one should be less or equal epsilon divided by 2. And using some algebra, we can get that alpha should be proportional to epsilon. And since eta is equal to alpha multiplied by gamma n from definition, we can say that eta should be proportional to epsilon. So in some, and gamma should be 1 over L. So in some sense, we have really tiny global server-side step size, which means we can control variance of partial participation by using this relaxation. And this could be beneficial if the second term is dominating in this bound. Any questions?
Yes, there are no questions.
Can you summarize in one sentence what is the main takeaway message of this slide? So
Okay.
You mentioned a lot of details, kind of main thing.
Okay, the main message here, when variance of client sampling is larger than local variance, it is beneficial to consider relaxation, which means it's beneficial to use small server-side step size to control this variance. And additionally, and at the same time, we can use a large client-side step size. And since we use gamma, okay.
Yeah, sorry, I thought you finished. So that was.
Okay, and since we use a large client-side step size, which is proportional 1 over L, this means that each local step is important, and this means that local steps actually helps in this regime. Okay, that was the overview of this consideration. And before I go to the experiments, I want to sum up all these considerations again. If we consider large server-side step size, in some sense we do. In some sense, we mimic. We just distributed gradient descent, and using small client-side step size, we control local variance. And if we use small server-side step size, we control global variance, which means we control variance of partial participation, and we cannot control both things at the same time, and depending on conditions of this variance, I mean local and global variance, we can use different strategies. But in practice, it's really hard to estimate what regime we have. Okay, and okay, now I want to show some experiments. So the main the main message from theory, the main insight is that both cases of server-side step size can be beneficial, small and large one. And it depends on variances. So, and it's really hard to estimate in advance before we start training. So, which means it's better to use some adaptive as the adaptive scheme for this step size. And here it's more experimental result. I mean, we do not have strong theory for adaptive step sizes, even for SGD, not even for random reshuffling, but here we just try. So we tried to use adaptive global step size eta and decreasing step size gamma here. And as we can see, this strategy outperforms the simple random federated random reshuffling significantly, as well as it outperforms adaptive gradient descent. And also we can see how our step sizes are changing. So we have decreasing gamma here, and as we can see, eta jumps from large regime to small regime, like during epochs, which means the method tries to control two types of variants at the same time. And I think this is a good insight to continue to understand this phenomena of decoupling. Okay, and let me conclude my talk. So we introduced Nastya, a new algorithm which includes random reshuffling to step size strategies and partial participation. So we provide theoretical guarantees for strongly convex, general convex, and non-convex functions. So we consider two regimes of small and large step sizes. And we have already shown that we have benefits in both regimes, and this theoretical consideration gave us some insights about adaptive step sizes and why they could be beneficial in practice. So thank you very much for your attention.